In section 2.3, we are learning about functions and their graphs. So we'll start out with the definition of a function. This is simply a rule that describes the relationship between two quantities, between two things. And we can describe these as an input and an output. And we typically think of this as equations in algebra. Right, so if we have an input, then we can, some quantitative value, some number. If we input that into the x value, then we'll get an output. We'll get some y value. And in business applications, some common examples of inputs could be, say, like the production level. Right, if you're producing something at a factory, you can determine how much profit you would make based on how many of those items that you make. So the production level would be the input, the profit would be the output. Another example is time being the input, right? If you know how much time passes by, then if you input that into the function, then you can determine what the population size of bacteria culture is. But anything that we can model using these functions to where we're in a sense we're predicting, right? If we know an input, then we can predict what that corresponding output will be. If we know the production level, then we can estimate how much profit that will have. If we know how much time passes by, then we can estimate the population size. These inputs, we'll refer to this as the more proper definition term, domain. So an input we're going to refer to as the domain. This is typically denoted by X. And the output we'll refer to that as the range. That's represented by Y or f of X. We're going to begin calling these equations that we've been working with a function. The only difference is instead of using y, we can use f of x to denote that it is a function. And so a function is you have only one output for each input, right? There's one y that corresponds to each x. In other words, we can say that the output associated with each input is unique. Now, back in your last algebra class, you may be able to refer back to the vertical line test, right? You determine whether an equation is a function, whether the graph represents a function or not based on the vertical line test, right? If a vertical line passes through that graph at exactly one point, that means it's a function. And that's what we're talking about here. The output associated with an input is unique. In other words, it would pass the vertical line test if we were to look at the graph of that function. All right, we're interested in being able to determine what the domain is for any given function. This gives us information, gives us characteristics about these functions. All right, so we want to be able to find the domain. Right, domain are all the inputs, right? What can we input into this function? What are all the possible x values that we can plug into that function and get a real valued output? Now, there are two restrictions that we'll use here. The first restriction is, we've already talked about this, we know we cannot divide by 0. That will help us to determine the domain. And the second restriction is that we cannot take the square root of a negative number. This will also help us to determine the domain. Okay, so let's look at some examples of functions and determine the domain, determine all the numbers that we can plug in to X. Okay, so I've put up 3 examples to where we are interested in finding the domain. Now, all 3 of these examples are functions, right? Anytime you see this f of x notation, right, this is telling you that it's a function, and this is synonymous with a y, right? I could have just as easily written y equal the square root of 2x minus 6, but the f of x notation is telling the reader that this is a function. We're only going to be working with functions in this class, though, right? So we want this to be a function. All right, but given these 3 functions, we want to find the domain of each function. To find the domain, we're going to refer to our 2 restrictions that we have listed down here at the bottom, is that we cannot divide by 0 and we cannot take the square root of a negative number. Okay, so in example 1, we have a function that involves a square root. Okay, so this follows restriction number 2. We cannot take the square root of a negative number. So that means whatever is underneath the square root better not be negative. All right, so we're saying 2x minus 6 cannot be negative in order for this function to have a real output, right? So we want to determine what the inputs must be. If 2x minus 6 cannot be negative, that means it's got to be greater than or equal to 0. And then we can solve this inequality by adding 6 to both sides, and then divide both sides by 2. So 6 divided by 2 is 3. So x greater than or equal to 3 would be all of the x values that I can plug into this function, and it would result in a real valued output, a real valued range. And when we're writing our domain, we want to write this in interval notation. Okay, interval notation, if that's something you're not familiar with, we have 2 numbers. The first number is where the domain starts, and the second number is where the domain stops. So in this case, so all of my numbers, x, must be greater than or equal to 3, right? So if I'm looking at a number line, where does this, where my x value start? Well, it's going to start at 3, right? I can be 3, the domain can be 3, and it can be anything greater than 3. It just can't be less than 3, right? Because say if x were to have been 2, if you were to try to plug 2 into this function, that'd been 2 times 2, which is 4. 4 minus 6 is negative 2, and we can't take the square root of negative 2. But as long as x is 3 or bigger than 3, that would result in a real valued solution, a real valued value of the function. So the interval notation, where does the solution start? Reading from left to right starts at 3. And we can include 3, so we're using the bracket. Bracket means that you're including that number. And so where does the domain stop? It goes everywhere to the right of 3. It can be greater than 3. And there's no restriction on the limit, so it goes to infinity, right? The domain, all these x values, you can enter a value in as large as you want to. We represent that by infinity. And parentheses around infinity, parentheses means that you are not including that number. And we can't include infinity because that's just a concept. It's not a real number. It's just a concept, meaning that there's no bound to the domain over to the right. Okay, so so we say this is the domain, 3 to infinity. Okay, so if we have a square root in the function, we set the term underneath the square root greater than or equal to 0. That's an always thing, no matter what the function is. If you see a square root, set what's underneath the square root greater than or equal to 0. Okay, now we'll move on to example number 2. In this case, we have a rational function. In other words, we have a function with a fraction. We have x plus 4 divided by x squared minus 9. And this would hit restriction number 1 to where we are not allowed to divide by 0. So we want to find all the values that would cause the denominator to be equal to 0. We can do that by setting that denominator equal to 0. Actually, what we're really trying to find is we're trying to find all the x values that would not cause the denominator to be equal to 0. So I'm going to use the not equal to notation instead of the equal to notation. Okay, this will give us the domain. All the x values that satisfies this statement will be in the domain. So x squared minus 9 not equal to 0. How do we solve for x here? Well, we have a quadratic equation because of the x squared. How do we solve for x in these quadratic equations? Well, we can use 3 approaches. We can either factor, we can use the quadratic formula, or we can complete the square. We want to factor anytime that we can factor, which we can in this case because we have a difference, because of the subtraction, we have a difference of squares, right? We're subtracting these 2 perfect squares because x squared is a perfect square, 9 is a perfect square, and this will factor into the square roots of those perfect squares, 1 parentheses being a plus, 1 parentheses being a minus. X plus 3 times x minus 3 cannot be equal to 0. So we set each of these factors not equal to 0. Okay, so x plus 3 cannot equal 0 and x minus 3 cannot equal 0. We can solve each of these equations for x. And we find that x cannot equal -3, x cannot equal 3, positive 3, because if you were to plug in -3 or positive 3 into this function, you would get 0 in the denominator. And we cannot divide by 0, so that means -3 and 3 are not in the domain, but everything else is. Okay, so how do we write that in interval notation? Right, again, if you like the number line, think about what this would look like on the number line. Right, so the x values can be anything except -3 and +3, right? So it can be anything to the left of -3, anywhere between -3 and 3, anywhere to the right of 3. So how would we write that? If we write this from left to right, right, where does the domain start? Well, it starts at -infinity because it never ends moving to the left, right? So that's represented by -infinity. And then it's got to stop at just to the left of -3. We can't include -3. So we want to use parentheses around that -3 because we're not including it. And then we're going to use a union here, right? Because you see the 3 different pieces on this real line, on this number line, 3 separate pieces. So we're going to take each piece at a time and use this union symbol to join them together. So this first shaded region to the left of -3, that's the -infinity, comma -3. And then union, now we have another shading between -3 and 3. And again, we are not including -3 or 3, so parentheses. And then we'll union again. We skip over 3, and we have another shaded region to the right of 3. And it goes to the right without end, so that's 3 comma infinity. So this would be the domain of this rational function for that example. Okay, and then finally for number 3, we have the function the square root of x squared plus 4. That should be a 4 there. Almost looks like a 9. But so how do we find the domain? Okay, we're at restriction number 2. Anytime we see a square root, we say that we cannot take the square root of a negative number. So we can set whatever's underneath the square root greater than or equal to 0. Okay, now before you try to solve this, stop and take a look, right? Use some common sense here, right? Some common mathematical sense, right? We've got x squared plus 4. Okay, what do you know about this? Look at x squared. If you square any number, it's going to be positive. And then if you add 4 to that positive number, it's still going to be positive. All right, so x squared plus 4 is always positive no matter what you plug into that x value. It's always going to be positive because this is a sum of squares, right? Not to be confused with a difference of squares. A difference of squares can be factored and solved for x. Sum of squares will never have a solution. So if you see the sum of these two perfect squares, you know that this will always be positive, and there's no restrictions on this function in regard to the domain. Right? There are no numbers that you can plug into x that would cause the square root to be negative. So therefore, the domain would be all real numbers. I can plug any number into this into the x value. So the domain is negative infinity to positive infinity. That represents all real numbers.